We're going to look at what happens when we have a circle that has lines and line segments that are interacting with the circle. Now we know that a circle is a set of points that is the same distance from a point that we call the center of the circle. If we have a line that intersects that circle in two places, that is called a secant line. And if we have a line segment that has as its endpoints 2 points that are on the circle, we have what's called a chord. A chord is actually a subset of a secant. A chord is the part of the secant that is contained either inside the circle or on the circle. Now we're going to look a little bit more closely at this idea of a chord. Since a chord is a line segment, we could construct a perpendicular bisector to that chord. And the perpendicular bisector of a chord will always intersect the center of a circle. Now what if we have not just one chord, but we have two chords? And we construct perpendicular bisectors to both of the chords. Well, since the perpendicular bisector of a chord will also contain the center of the circle, and we have two perpendicular bisectors that both have to contain the center of the circle, we know that the center of the circle is contained at the intersection of the two perpendicular bisectors. Now let's suppose that our two chords are intersecting. And since they intersect, the chords are now being divided up into smaller pieces, not equal pieces, just smaller pieces. So let's say that we call the length of one part of this chord A and the length of the other part B. So together A and B are making up the length of that chord. And let's suppose that the other chord has been split into two pieces, and one of those pieces has a length of C and the other has a length of D. There's some proportionality that goes on when we have two intersecting chords, and that's expressed in this equation. That if we take the products of the lengths that we have divided our chords into and we multiply those numbers together. So A times B, the product of those two lengths A and B, and the product of the two lengths C and D, those products will always be equal to each other. Now suppose that this length is 6 and this length is 2. So that chord was 8 units long and it was split into two pieces. One is 6 units long, the other is 2 units long. And let's suppose the other chord has a part that is 3 units long, and we want to know how long the last part is. So we need to know what D is. Well, we know that the product of the two lengths on the one chord, so 6 times 2, has to equal the product of the two lengths on the other chord, so that's 3 times D, which would lead us to the result that D has to equal 4. Now there's something else interesting that goes on because of this proportionality between these lengths, and that is that we can create two triangles by connecting up the endpoints of the line segments that are forming the chords. These two triangles are similar triangles. So we know that similar triangles have 3 pairs of angles that are congruent. So let's think about which angles are the congruent angles. We know that these two angles have to be congruent because they're vertical angles. And if we can find a pair of angles, one from each of the triangles, that are on the same side as that point of intersection where the two triangles intersect, those two angles will also be congruent. So that means these two angles that are in blue have to be congruent angles. And these two angles that are marked in red are on the same side of the point of intersection of the two triangles. So they are also congruent. Now, how can that help us? Well, suppose that we have these two chords that were used to define the two triangles, and we know that this angle is a 30-degree angle. That would tell us that we also have a 30-degree angle in the other triangle. Now, without a little more information, we can't find the measures of the other two triangles. But if we knew one of the other angles, we would be able to figure out all of the angles in both triangles. Now let's say we have a circle and there's a line that intersects that circle, but that line is only intersecting that circle in a single point, not 2 points. If we have a line that intersects a circle in a single point, that is called a tangent line to the circle. And there's still some interesting things that go on with tangent lines. For example, suppose we construct a perpendicular to this tangent line through that point where the line is tangent to the circle. That perpendicular will also intersect the center of the circle. Now suppose instead of having just one tangent line, we have two tangent lines and they intersect each other as well. We know that any perpendicular to a tangent line that goes through the point of tangency will also go through the center of the circle. Now if we also construct a line segment that connects the center of the circle with the point of intersection of the two tangent lines, what you can see is that we have two triangles that are created. These triangles will be congruent, which means we will be able to find 3 pairs of angles that are congruent and 3 pairs of sides that are congruent. So in this case, if you look at these two angles that were formed by the two tangent lines and that line segment that we used as to connect up that intersection point and the center, those two angles will be congruent angles. And in fact, if we're looking for pairs of congruent sides, obviously the two sides that are both a radius of the circle must be congruent, and the side that the two triangles share must be congruent, and these two sides must also be congruent on our two triangles. So as usual, we'll get to practice a few problems in class and see how we can make all of these properties work to give us information about the triangles and the angles that are formed when we have lines that intersect circles.